telling about our today's speaker. It's my great pleasure to present you Sara Majetich uh, with her talk Magnetization Dynamics in Artificial Spin Ice based on magnetic tunnel junctions. And with this one slide, I would like to briefly tell you about her biography. Sara Majetich is a professor in physics department at Carnegie Mellon University in Pittsburgh with courtesy appointments in electrical and computer engineering and material science and engineering. Her research focuses on nanomagnetism. It has included studies of collective magnetic behavior in nanoparticle assemblies through electron microscopy and small angle neutron scattering, and magnetoresistance measurements on single nanoparticles. It also includes investigation of magnetoresistance and current or voltage-induced switching in small magnetic tunnel junctions. She is a fellow of the IEEE and the APS and has authored over 200 papers. She has been active in the IEEE Magnetic Society, where she has been a distinguished lecturer, education committee chair, and secretary. She is currently the president-elect of the IEEE Magnetic Society. And with this brief introduction, I would like to pass the microphone to you, Sara. Please.
Thank you very much. Okay, so you're going to close. Okay. Go. Okay, can everyone see this? Good.
Yes.
So thank you very much. It's a pleasure to get an opportunity to tell you a little bit about our work, but also to get to know some of you a bit. Some of you I've known by their names through the program, the initiative that the IEEE Magnetic Society has to support magnetic researchers in Ukraine. But I've never been to Kharkiv, but I have been to Ukraine. So I'm thinking about all of you and wishing you well. Today I'm going to talk about our work with magnetic tunnel junctions, looking at magnetization dynamics. And so I will explain what this device is, which is a magnetic tunnel junction that has two ferromagnetic layers separated by a tunnel barrier. Here's an experimental scanning electron microscopy image of an array of these tunnel junctions and their magnetization directions. And in the middle is a trace of the resistance over time showing the dynamics of one of these tunnel junctions. So I'll explain all of that. But first, Heroim Slava. I've learned a lot about Kharkiv after the war started. Didn't realize how much physics went on and continues to go on there. But you know, as a great history and a lot of scientists, including a lot of scientists who do magnetism. So 5 months after I visited Ukraine, the war started, and I and a lot of others in the Magnetic Society thought about how many people that we knew who were stuck, who were dealing with very difficult times. And so with Andrei Chumak from University of Vienna in the lead, we created a program from the IEEE Magnetic Society to support magnetics researchers who are based in Ukraine. The grants are small, but we've done this. This was discussed in Science. We are continuing with this program this year, and they just submitted the request for next year, which I will discuss at a meeting with the IEEE at the end of June. So hopefully it continues. But I also wanted to say that there's a lot of support for Ukraine in Pittsburgh. That has nothing to do with the Magnetic Society. This is one street in Pittsburgh that has 11 different Ukrainian flags displayed. And as far as I know, there is one Ukrainian guy who lives on the street, Sergei Frolov. The other people are not Ukrainian, probably have not been to Ukraine, but there's a lot of support for you. So, and here is down here is a demonstration that was held in March. So a lot of support, hoping the war ends and also hoping that Ukrainian science comes back. Okay, so back to the science here. This is the quantum seminar, so I wanted to make it clear what aspects of what I'll discuss are quantum and what are not. And all of magnetism is, in a sense, quantum. And these devices that he studied are magnetic tunnel junctions, so they have quantum mechanical tunneling. This tunnel barrier is very thin, 1 nanometer magnesium oxide layer. Turns out that there's a very special connection between this cobalt iron based alloy and magnesium oxide. If it's crystallized in a certain direction, the tunnel barrier has a spin filtering effect, even though it's not magnetic at all. So there's a reason that people working in the magnetics area like this combination for their basic device. I'll be talking about how we use it, and that's where if we're looking at current that is coming through one of these layers that's uniformly magnetized, then you get spin polarization. And if the second layer is magnetized parallel to it, there's more tunnel current than if it's anti-parallel. So this difference in the electrical resistance tells you about the magnetic state. So it's a way of reading the state, the magnetic state of your tunnel junction. Because this is non-volatile, this takes no energy to store it and very low energy to read its state. So this is one of the reasons people are interested in magnetic tunnel junctions. I should also point out that this relative difference in resistance can be up to 400%. The devices I'll tell you about today are not 400%, they're more like 40%, but still the signal to noise ratio is good enough to use in devices. And again, another way to look at tunnel magnetoresistance is to think about what happens to the electrons that are passing through. And here you have spin up and spin down electrons. You quantize the axis of spin by passing them through a uniformly magnetized layer. But then those that have spin that's parallel to the local magnetization have fewer scattering events than those are anti-parallel. And if you have two layers that have parallel magnetization, then the spins that have electrons that have spin parallel to that will have relatively little scattering in both layers, and the ones anti-parallel would have a lot of scattering. So in the parallel resistance channel models, your spin to the left electrons have low resistance the whole way through. The other channel with spin to the right has high resistance, and so the tunnel current is going to shunt through the low resistance path. And overall, you get a smaller resistance than if you have anti-parallel magnetic orientations in the layer. This equivalent resistor network was something for students to pay attention to, is that this is something that was used by Albert Fert when he was a graduate student to explain his data for single magnetic layers and their electrical resistance as a function of temperature. Fert went on to discover giant magnetoresistance, where you have a metal, non-magnetic metal barrier. And he was one of the two winners of the Nobel Prize in 2007 for giant magnetoresistance. So if you want to look at this phenomenon in a more quantum mechanical way, you will look at the density of states between the different layers. And here, if you start with one layer that's magnetized one way, If it's a ferromagnet, the density of states for spins magnetized to the right and to the left is going to be offset by the exchange energy, and there can be different numbers of available spins at the Fermi energy. If you go to tunnel to another layer with the same magnetic orientation, you go from a relatively large number of states to a large number of empty states. So there'll be a lot of current. However, if you go to a layer that has the opposite magnetization, you would go from, say, a large number of states with spin to the left, and there's not as many states available to go into in the other layer. So both the parallel resistance model and the density of states model explain the difference in resistance depending on whether the magnetization of these levels are parallel or anti-parallel. And that's what I'm going to build on in the rest of the talk. So before I do that, I want to say something about what is not quantum that I'm talking about. And it's very tempting to look at these resistance traces as a function of time and think, oh, there's something that corresponds to a 1 and a 0, but it's not a 1 and a 0 at the same time. It's not a superposition state. It's really in one state or the other. And this is modeled with monodomain nanoparticles as going over an energy barrier to rotate all of the spins from one state to another. In dynamics, we think about the rate of attempting to go over the barrier from one state or another. And experiments by many, many people have shown in particles, but also in tunnel junctions, that you get a rate that depends on this energy barrier. You can tune it with an external field or with the temperature. So this is a true activation to get from one state to another, not tunneling through the barrier. So not like a molecular magnet. All the data that I will show you is taken at 300 Kelvin. So again, that's not typical of quantum experiments, but it is very good if you want to have devices that take advantage of quantum physics through the MGO tunnel barrier. So what I'll tell you about today are first to go through some important features of our tunnel junctions when they're super paramagnetic, and to introduce artificial spin ice, which our group is making out of super paramagnetic tunnel junctions, and then go on to look at the dynamics and modeling and relevance to computation. So we started out looking at isolated tunnel junctions that were very small enough to be thermally unstable with respect to the magnetic state. And these first tunnel junctions were magnetized perpendicular to the plane rather than in the plane, like the ones I'll tell you about later. But that's not critical here. If we apply a magnetic field and measure the electrical resistance through this device, if we ramp the field, we get this black curve, and it starts at one resistance level and suddenly switches up, saturates. If we turn down the saturation field, it switches down very abruptly. But if you sit at one particular field in this open area and measure as a function of time, you see that it's not a fixed value. It has thermal fluctuations between two levels. These are offset. And you go over a relatively small range of field from a state where it's mostly in the low resistance or parallel magnetization state to the high resistance most of the time, mostly in the anti-parallel state. And if you took the time average of each of these colored curves, you would get the red S-shaped curve. That's the sigmoid curve that's very important for any probabilistic computing application. So people in quantum computing have different metrics. For probabilistic computing, you want this S-shaped curve that you can tune. But you want to be able to tune it not with a field, because it would be hard to apply a different field to all of your different devices, but fairly straightforward with today's electronics to apply an independent current or voltage. With magnetic devices, in particular the magnetic tunnel junctions, there are three good ways to do this. There is voltage-controlled magnetic anisotropy, which works if you have perpendicular magnetization. It's very, very low energy. There's spin transfer torque. We're using a large spin polarized current to switch the state, or in this case, to tune the position on the sigmoid curve. And there is lower energy spin orbit torque, where you're using a pure spin current generated by a real current through a heavy metal. The difficulty of the spin orbit torque is that it requires a three-terminal device. And if you're wanting to use, say, a crossbar array for memory or logic, this is less convenient. But let me just say a little bit about the properties. Again, you want your devices to be faster. The field tunable perpendicular device I showed you earlier was fluctuating on the time scale of seconds. If you change that magnetization direction to in plane, you speed it up. And so here we've got something that can be tuned with the voltage, and it's having fluctuations here we're showing on the microsecond scale. We've measured down to 200 nanoseconds, and actually you could go faster, but it's limited by our existing electronics. So the structure that we use for our individual devices has a lot of layers in it. I've just showed the two magnetic layers, but our devices actually have quite a few layers here. When my students start, they get confused by this. They ask, why are there so many layers? And explain the reason for each one. I'm not going to go into all of the details here. But once the students get started, then when they go to conferences and they see somebody else put up a diagram like this, they pay attention to the details of all of these different layers. This combination here shown in red is the fixed layer. The antiferromagnet iridium manganese helps to pin the ferromagnetic cobalt iron, which is in a synthetic antiferromagnet, again, in order to stabilize this so that this magnetization stays fixed. It's not changing in our experiments. The blue layer is a single cobalt iron boron layer, and it is switching back and forth during the experiments. You notice also that the blue layer is thinner in diameter. This red layer is in fact continuous over the entire substrate. I'll explain the reason for that. But first, I'll show you what happens if you pattern the entire thing all the way through and make a 60 nanometer circular tunnel junction. You see a resistance versus applied field curve that's showing some telegraphing as we scan. So compared with the earlier curve where it stayed stable and then switched up just once and switched back, here the device is switching so fast that over this time period where it's scanning through a field, it's switching back and forth, and you're seeing that in real time. So we're seeing this telegraphing, but the telegraphing for the fully patterned device is not occurring at zero field, where it would be low energy, but at 25 to 30 Ørsted, where you'd have to apply an external field to make this work for probabilistic computing. You don't want that. If you go back and you don't pattern this fixed layer, then the fringe field drops down from 30 Ørsted to just a few Ørsted. And then this telegraphing region extends across 0. So that's an important trick. So that's our building block in terms of the magnetic tunnel junction. This talk is about combining the tunnel junctions with artificial spin ice. So artificial spin ice was first demonstrated by Peter Schiffer's group he was then at Penn State, he's now at Princeton. And what he did was to use lithography to pattern permalloy or nickel iron alloy islands with some shape anisotropy. And these are a few hundred nanometers in size. But if he did magnetic force microscopy to look at which way these islands were magnetized, he saw there were different patterns. And so at MFM, you're sensitive to the perpendicular magnetization. So a north pole looks black and a south pole looks white, or vice versa. And if we look at a node at the intersection of these 4 islands that are interacting only through magnetostatics, we see that there's 2, say, north poles pointing in and 2 north poles pointing out of a node. So that follows the spin ice rule that says that you should have in square ice 2 spins in and 2 spins out for the lowest energy. Over here in blue, we also have 2 spins in and 2 spins out, but in a different configuration than the pink. However, in the green, we have 3 spins in and 1 spin out. So that's different. That is a low energy excitation. And if you look at the different nodes, there's 16 possibilities for square ice. The reds are the lowest energy states. Then blue shows that you can have a fair number statistically of excited states. And the green are the really excited states with all the spins pointing in or all pointing out. Now, the relative energies depend on the size and the shape and the spacing of the nanomagnets, but you can calculate that. And that's what we did for our circular 60 nanometer dots with 90 nanometers center to center spacing. Going this way, edge to edge, we've got 25 nanometers here. So gives you an idea of the length scale of the coupling. And in this case, we've got 1 state with 2 spins in and 2 out. That's the ground state. There's another state that's observed. It's no longer degenerate for the shape and the spacing and size. It's a little bit higher, but just a few kT. And then we have the more excited states. So you can calculate this. Again, other people did this first. We used MEMAX3 for our simulations. And what we're wanting to do with our spin ice is to look at it for a type of probabilistic computing, specifically seeing whether we could use the spin ice for reservoir computing, where the advantage would be that we don't have to hardwire each of these little tunnel junctions because they're magnetostatically coupled with one another. So unlike some types of reservoir computing where including reservoir computing that's using and probabilistic computing using magnetic tunnel junctions, in those cases, such as the work by Hyun-Soo Young at National University of Singapore, each device is hardwired electrically. And the advantage that you get to that is that you can reprogram the weights of every device in the reservoir. The disadvantage is that in order to reprogram, you need to use energy to do this, to switch the states or to hold them at a particular state. And so if we're thinking about using this as a neural network so that you could do AI, AI is a power hog. We're looking for ways to reduce the energy requirements, but get the same kind of functionality. So this is not something I will demonstrate today, but this is our vision for what we would like to do. And again, right now, people are doing this with CMOS, but CMOS needs a lot of energy in order to do this. CMOS would also be a lot bigger, or this could be a lot smaller footprint than CMOS. Faster would probably be on the same time scale within an order of magnitude. It is electrically compatible with CMOS. So there's lots of interesting things to look ahead to. But first, we need to understand how this works and how to control it. So want to say something about the dynamics and what we know so far. So compared with the prior work on artificial spin ice, we're using smaller nanomagnets. So instead of hundreds of nanometers, we've got 60 nanometers. We're making them closer together. People have been able to look at images of the artificial spin ice using MFM, which I showed, but also a lot of work with X-ray magnetic circular dichroism. And beautiful, beautiful images. I'll show you some later. But this relaxation occurs over hours. They can control the motion of the excitations with the magnetic field. But if you're thinking in terms of a device, you want it smaller, you want it faster, and you want to have some sort of electrical control of the inputs and outputs. So that's what we've used to design our artificial spin ice. This is what it looks like. We've got these individual pillars, but now they're closely spaced. And this is a top view SEM image. If we look at the schematic of the side view, I said that the fixed layer was continuous. It's under all of these dots. It's the same fixed layer, the same magnetization, and each one of them has a free layer, 60 nanometers in diameter, and the free layer of one could be a different direction than the free layer of another. We're able to do single dot, single pillar electrical measurements of the resistance as a function of field and as a function of time using conductive atomic force microscopy. So this is different from scanning tunneling microscopy because we can do this in air. We don't have don't need a high vacuum. We have direct contact because the tunnel barrier is not the vacuum, the tunnel barrier is built into the device. So the benefit, in addition to ease of measurement, is that as we scan across the devices, if we go from a conducting region, we can measure the resistance dynamics. Sorry. We go onto the non-conducting silicon nitride barrier in between, and we don't crash our tip. If you did STM in ultra high vacuum, it would be getting closer and closer to try to get a certain tunnel current threshold, and you wouldn't reach it because this is an insulator. So we can scan over a mixture of conducting and non-conducting areas. So it's a really useful tool for that. We use it for magnetoresistance. One caveat is that when you're doing this, there's a certain contact resistance associated with making electrical contact with one device, then the next, then the next. And that's about 200 ohms. And with the resistance of a tunnel junction, 200 ohms is small. And so we can neglect that. But if you had an all metallic device, the contact resistance could be a problem. So what do we see? When we look at the individual devices, we look at the resistance and we scan the field in the X direction, and we see these blue curves here, scan up, scan back. And we get these S-shaped curves for all of them. At first they look similar, but then you notice that there's small differences. This one has clear telegraphing and it's sharper. than this one, which is more curved. And we also notice that there's a pattern of which ones have the boxier look, the sharp jump, and which ones have more curvature. And the boxier ones, we call these X devices because they're magnetized along the X direction. And these other ones have a preferential magnetization along the Y direction. If we'd have a Y field, they would look boxy, and these would look curved. But if we have an X field, we get this curved behavior that's consistent with what you would expect for a ferromagnet with field along a hard axis, whereas the X devices are more characteristic of a ferromagnet with a field along the easy axis. And just to review, or for people who aren't in the magnetics area, if you've got a field along an easy axis, which can be defined by the shape for these elongated nanomagnets in traditional spin ice, or here by the magnetocrystalline anisotropy, which is very low for cobalt iron boron, you would get a switch up and a switch down. This is just happening very, very quickly. So we see the telegraphing. We see telegraphing at or near zero field, which is good for low energy. If we have these other devices, they have more curvature. And what is happening is as you apply a field in the X direction to a device that wants to be magnetized along Y, you're rotating that moment away from Y until you saturate and it really is along X or minus X. And you get this gradual rotation. So very different behavior, even though to first order the curves look similar. We can go farther with magnetoresistance because with these two layers, there's a relation between the angle, the relative angle of the fixed and free layer moments and the measured resistance. So if we have an X device, it will have nearest neighbors that are all Y devices. So should have magnetization that's jumping back and forth more or less perpendicular to it. And depending on the combination, they're going to give a net magnetostatic field at this X device. What we observe experimentally is that the X device resistance jumps between more or less between two different layers, two different levels at zero field. So this is happening just from KT at room temperature. And if we decompose this into the angles that this central moment is spending time in, most of the time it's either at 0 degrees or 180 degrees. So that makes sense. There's a little asymmetry because the fixed layer has a small fringe field that we haven't canceled, but that's about 8 Ørsted, very small. If we look at these Y devices, which will have 4 X nearest neighbors with magnetic moments jumping back and forth perpendicular to it, we saw a real surprise. And looking at the same device at different times, the resistance could be this red curve showing some spikes to lower resistance, but then a few seconds later, it could, or hundreds of milliseconds later, could jump to a different level. Same device, just jumps to a different baseline, jumps to a third baseline, jumps back and forth, but is fairly constant other than these short excursions, mostly to lower resistance. Now, when we convert that to angle, we see that the same device is not plus or minus 90 degrees, but it can go to plus or minus 56 or plus or minus 153, and we can see that through magnetoresistance. So what we're seeing and what I indicate with this black wedge is that the moment of the Y devices is canting as a function of time. It finds some relatively stable baseline levels, But from that baseline, it has excursions going to lower resistance or lower angle, closer to that of the fringe field from the fixed layer, but they're short-lived. And unlike for the X devices, which are going between 0 and 180 degrees, these spikes have different amplitude. Some are small, some are big. There's no fixed threshold. Qualitatively, it's about the same jump, but not exactly every time. So this was really surprising to us. What we could say, knowing what I explained earlier, is that the X devices act a lot like what you would expect for a monodomain particle with two relatively low energy configurations, field due to the fixed layer favoring one slightly over the other, an energy barrier in between them. This device, this X device, is going to spend most of its time in one of these two low energy states. To go in between it, it has to go through a high energy state where the magnetic moment is perpendicular to the field, up or down, but it should not spend a lot of time there. Whereas these Y devices are starting in this high energy state. So they don't have the option to go down to a low energy state because of the local field. They act more like what would be called an easy plane model, where the moment can rotate at different angles within the plane, doesn't go perpendicular to the plane. If we put in the coupling field, there's a slight preference for one or another, but it doesn't explain what we're observing experimentally, which is that we don't have a continuum, we have specific preferred levels, and it doesn't explain these spikes. So we have to go further to try to understand that. But first, I want to say a little bit more about what we see from the experimental data. Starting with the X devices, when you make spin ice, you're expecting the dynamics to be different because of the magnetostatic interactions. And if you look at a long time, not microseconds, but seconds, hundreds of seconds, you see that the same device will telegraph, slow down, speed up, slow down, speed up, slow down, etc. And it has periods where nothing happens for 10 seconds, just stays in a particular state. And the way that we think about this is to go back to the simple picture of a single particle going over a barrier and coming back. It's stabilized in one state or another, parallel or anti-parallel, by a Zeeman field. Usually, this is due to an external applied field, but in the spin ice, this is changing when the neighbor spins, the neighbor MTJs are reversing their magnetic direction. So this magnitude gets bigger or smaller. You can trap in one state, or you can destabilize it so it gets over the barrier faster. And this is what we think is happening over time with the X devices. One way to quantify this, and we've used this earlier for isolated devices, is to do an autocorrelation where you take the signal time-dependent resistance and subtract the average resistance, multiply that by the time-dependent resistance at a later time, and normalize it. And this function decays logarithmically, and there's a characteristic decay time. In fact, if we take windows where we think the telegraphing is relatively uniform, we see something that's single exponential or close to single exponential, maybe a little curvature in here, with relaxation times on the order of a few milliseconds. But you can't do this for the other types of devices, the Y devices, where the autocorrelation just gives a mess. And so we used a different approach here based on dwell time distributions. If you have a stochastic process, then the dwell time distribution analysis is equivalent. A dwell time is the time in a baseline before it departs from the baseline. And if you measure all these different dwell times, you can build up a histogram. And we made histograms for each different state, looking over 60,000 windows of this behavior. So we've got as good a statistics as we possibly can. But in terms of thinking of the behavior, the probability of a given dwell time, if you have like a simple first order differential equation, should decay exponentially, e minus the dwell time over this average decay time. If you have a distribution, or sorry, if we have different dwell times, then you don't see this single exponential decay. So what we find, and again, this is very preliminary data. My student Connor Sullivan showed it to me yesterday, but I think it makes the point that if we look at all the different levels that we can observe, we do not see a single exponential decay. So that would be this dashed line here. The departure from single exponential decay just means that you have interaction effects. So if you want to do reservoir computing, you want interaction effects and you want to be able to control them. You want to be able to design them in. The X devices have very steep slopes. Those are these A and B here. So they're reasonably linear, some departure, not strictly, but closer to single exponential than the Y devices, which can be very steep slope. The slope is what's telling you about the relaxation time. Some of them are clearly different. And so what's interesting to us is what makes them different? What is it about these particular states that gives them some built-in memory of where they've been in and might be useful for reservoir computing? For example, if you wanted to use short-term memory for voice recognition, speech recognition. So in this case, we look at the relative angle compared to the fixed layer fringe field. And these really slow relaxation states are always looking more than plus or minus 90 degrees. So, or sorry, less than plus or minus 90 degrees. More than 90 degrees, those are very rapidly decaying. So there's clues to what is happening, but there's also a lot of additional information here that we want to understand to engineer our spin ice. One way to imagine this is if you have a distribution of dwell times that gives you a stretch exponential like behavior, that you could have a more physics-based model if you just integrate the contributions for different relaxation times. But that requires that you have some sort of assumption about what the distribution of relaxation times would be. This is going to be something that we can calculate with Mumax 3 for a spin ice. We're in the process of doing that now, but we're also in the process of fitting the data. What I can show you is what does not work. We do not have a uniform distribution of relaxation times between a minimum and a maximum value. If you did, you would get these dashed curves. Here's the experimental data for two different states, obviously quite different. What we can say qualitatively is that there are more short dwell times. The long dwell times are less common, but that's something that we want to understand the physics of. And I want to point out, one of the interesting things that's come out of this work is the ability to differentiate uniform distribution, which is what has been used, what has been assumed in all prior magnetics models of what's called magnetic viscosity. So, for example, if you have magnetic relaxation of an ensemble of identical nanoparticles, monodomain, Louis Néel said the magnetization will decay with a single exponential. People who work with magnetic recording media, where you have magnetic grains, all monodomain, but they have some weak interactions. They don't see exponential decay, they see logarithmic decay. So interactions make a huge difference in the dynamics. This is one of the reasons that being able to measure dynamics gives such a unique insight to what is going on in nanomagnets. So I won't say more about the dynamics, but I wanted to say something about the metastable states that we're observing and how we understand what leads to these baselines. So the simplest magnetostatic model of the local field would have your central spin and 4 nearest neighbors. And there are 5 different ways that you can arrange them. The traditional ASI ground state has the central spin perpendicular plus or minus 90 degrees. This is what is seen with the elongated nanomagnets exclusively. If you go to case 2, you get a saturated state. We don't have a big field, so we don't see much of this. What we do see a lot of is this canting state. These are the different levels that we get if 3 of your neighbors point one way and 1 points the opposite direction. And then we get cases where the fields of the nearest neighbors exactly cancels. But of course, that just means that you need next nearest neighbors to break symmetry. So simple model. And my student, Connor, again, looked at building on this model with next nearest neighbors, north and south. They can add as much as 10 or 15 Ørsted to the central spin field, east and west, meaning along the east-west line being along the fringe field direction. They only add half as much as you expect for point dipoles. And the quick summary is there's a lot of different canting angles that you can get. These get perturbed, so I don't want to go into the details, but just to point out that the near neighbor interactions and next nearest neighbor interactions predict a lot of possible canting states, and we observe a lot of possible canting states. MEMAX3 lets us calculate the energies, and in fact, there are a lot of states within a few kT of the ground state. More importantly, many of these states shown in red or in brown violate the spin ice rules that say there should be 2 spins in and 2 spins out. So these are the excitations that are going to be useful for adding complexity in our reservoir. I should also point out that we can associate the measured resistance for the baseline with these different levels with local spin configurations, some of which have no canting, some of which have canting away from the fringe field towards the fringe field. So this is one of the long-lived states that has a very slow relaxation time. These have short relaxation times of a few nanoseconds. So this helps to give you memory. And however, these magnetostatic calculations do not explain why you have spikes. The spikes, we believe, are associated with this easy axis, hard axis behavior that with a sharp magnetization or resistance curve, you get actual switching between 0 and 180 degrees back and forth. With the hard axis curve, you're not switching. The magnitude of the fields that you get from these near neighbors interactions is in this range where you're getting rotation, but you're not saturating at either of these states. And in fact, saturation in this case would be lying along the X direction. That's a very high energy state. So we think we understand the features of our dynamics of the artificial spin ice in a square lattice. Now, what can we do with it? And here there's a lot of literature. And I'm coming to the last part. There's a lot of literature where people have chosen flashy nomenclature of magnetic monopoles. And you see this in bulk spin ice as well. I don't like the terminology, but it gets you on the cover of Nature, so I understand why it's very popular. The idea is not to violate the laws of physics, but to treat a magnetic moment as having magnetic charges, plus and minus, so that you have a dipole here. This is fake charge of the North and the South Pole. But overall, you have net charge 0 for the dipole. Now, if you look at a node where 4 spins or 4 dipoles meet, and you sum the total charge at that node, if you follow the ice rule, 2 spins in, 2 spins out, the net charge is 0. So this is a stable state. This turns out to be a type 2 node. But in some cases, you have, say, 3 spins pointing in and 1 spin pointing out. You have a net charge at this node, and so that's an unstable state or a higher energy state. This is what is called the monopole, whether it's type 3 or type 4, that's considered a monopole. If you imagine what happens to the central spin that has interactions, part of a type 2 node and a type 3 node, if it reverses thermally, now this node is type 3 and that's type 2. So it's going to be in a high energy state. And the only way that it can relax is if one of these side spins, one of the neighbor spins also flips. So that could lead to fast dynamics. There's been some very nice work done by Chris Layton's group looking at square ice, traditional ice, and working out a phase diagram where, depending on the field that you apply in the X or the Y direction, you can initialize your ice to have mostly type 2 nodes, or lots of papers have been written about how to use AC demagnetization to get mostly type 1, but it's actually quite tricky to get a true ground state. In our case, we don't really care. We assume that at room temperature, you're going to have excitations, and we want excitations. We just want to be able to identify them with resistance and control their injection and detection also with resistance. So we are in the regime for what I've talked about here of the monopole plasma, where you've got individual excitations. If you have neutral spin ice, and you create a pair of excitations, 2 types of monopoles. Here was 3 in, 1 out. Here's with 3 out, 1 in. And they move through the lattice. And what we've been able to see is that through our resistance, we can differentiate the type of monopoles that you have. We've got more flavors than just 3 in and 3 out. We've got different Canting angles as well, but we can see this with resistance. So we think this is a useful tool to use to study artificial spin ice. What people do with this with magnetic fields, again, this is with the traditional ice and an external magnetic field, they can move the monopoles in a preferential direction. Again, this is imaged over hours. What we would like to do is to inject monopoles with spin transfer torque at the edge and have them move. Here's some other work. The last work was by Laura Heiderman's group. This work is by Nicholas Guy's group, where they've done a lot of simulations looking at the motion of separation of the pair of monopoles. Chris Marrow's group has also looked with traditional spin ice and X-ray imaging. They've done some micromagnetics calculations of the energy barriers. What we want to do is to take our smaller, faster spin ice and do the same sort of things. Ideally, if you wanted to make a neural network, what you would do is to have independent inputs where you could eject, create type 3 nodes and let them diffuse. If you could inject them close together, you could look at their interactions, and we could do this with synchronized resistance measurements, which we've already done on independent tunnel junctions. So this is the future direction that we're looking at. So I thank you for your attention. What I've shown is that you can combine tunnel junctions and artificial spin ice to see interesting dynamics. Some of the dynamics are surprising with the canting of the moments. That is something you would lose if you had elongated nanomagnets. But if you had elongated nanomagnets, they'd be slower in their dynamics and you want them fast. So having them fast and understanding how to control them, I think, is the way forward. So thank you very much.
Thank you so much, Sarah, for the very beautiful talk, full of nice results and a review of other works. Now, the talk of Professor Majetich is open for questions. Yes, Andrei, please.
Yeah, thank you for the results and the interesting talk. So I'm wondering for example, in the autocorrelation time analysis, did you perform some averaging over samples, or it was performed on a single experimental?
Whenever we do autocorrelation, we use a single sample.
Yeah,
Right.
and I'm wondering, does it differ from sample to sample?
Yes. Well, I think you
details?
can see that with the SEM image. They're the same nominal size, but they're not perfect. There are variations, and so in a previous project where we had bigger spacing between tunnel junctions, we did comparison of 100 devices with each other, and there definitely are device-to-device variations. Part of that was feedback for the processing. What we found was the ones at the edges were different from the ones in the center. So all the measurements that I showed you here are for devices that are in the center, and where I compare the results of, say the different states for a Y device, they're all the same device, the exact same device. Otherwise, I would, with like the very small differences in slopes or in autocorrelations, I would be concerned about the comparison. It is a big issue for the electronics industry to make devices where you have a really narrow distribution of behavior. I know the people who are looking at MRAM, magnetic RAM. We used to meet, we had a 5-year project, and the people from IBM would say, what is your write error rate? What is your Six Sigma? What is, and at a university, you're not making devices at the same level that you could at IBM. My last 3 students are working at Intel. So they have the facilities to make really high quality devices, but all of that is automated. Whereas at a university, it's done by a graduate student or a postdoc associate going to the clean room and slaving away, making these devices. So what we're trying to do is to understand what is the physics, and how does the physics connect with the engineering? What are the challenges and what are the benefits that if companies took over, they could make lots of progress with?
Thank you very much.
Speaking about, I'd like to ask about electrical compatibility with CMOS.
Yes.
How do you reach it, and which benefits do you have from this?
Okay. So certainly you want to have compatibility with CMOS or it's not going to move forward. So we grow these stacks, or I should point out Zhishang Zhang from KAUST, his group grows the stacks. We do the patterning and the measurements. They're all deposited on silicon wafers. And when we look at oops, we have conducting layers to make the electrical contacts on the bottom and on the top to connect with CMOS. Let me just show you at the very end. Okay, these devices here are on a silicon wafer, and each one of these flower patterns has a single magnetic tunnel junction buried in the center. It has 4 electrodes that connect to the top and 4 electrodes, the diagonals, that connect to the bottom. And this is on a little chip that we then wire bond. Again, this is university level making of devices, but we integrate that with CMOS. If we were Intel or IBM, this would all be, just multiple layers. And so, but we make the vias to make the connections to top and bottom electrodes. So there's potential for not just for integration with CMOS, but for on-chip integration with CMOS, which I think is where the real advantage is. If you want to make progress, having memory in computing is an important step forward.
Yeah, thank you. There's Yaroslav Bazali, please.
Yeah, thank you. Thank you. Very a lot of interesting ideas. And one thing I wanted to ask is when you think about traditional spin-ice, then
Yes.
these monopoles, they seem to be related to the fact that there are only whatever 16 positions. And now when you have circular elements, then the direction of magnetization can be anything. So from the theoretical point of view, does that mean that this idea of monopoles is sort of diluted and doesn't,
I guess
is no longer so appealing, or is it still some kind of a proof that you will still have a description in terms of monopoles?
Yes, very good question. And we've asked ourselves that a lot. What I would say is I would define anything where the net charge around a node is non-zero as a monopole.
Mhm.
But if we look at the different states, see, all these here, the A2 and A4 and A5, those have 90-degree plus or minus 90-degree angles. So those would be a traditional monopole. But all these other ones are intermediate states that have canting. They're still, the brown ones are still monopoles. So you've got more kinds of monopoles, including quite a few at low energy, relatively low energy, that are accessible. So I think, again, I think it depends on what you're wanting to do with this. I would feel better calling them all excitations than monopoles. I may not be able to change the field's preference for terminology, but we just view them as excitations. What you want to be able to do in a lattice is have an excitation here, communicate and change the spin at a neighboring site, and have that branch out. That's what gives the complexity, the nonlinear response that we're looking for, either in probabilistic computing or in reservoir computing. So for us, we don't really care. For us, what we do care about is how do you introduce memory into your system in addition to nonlinearity, and how do you control the memory? So, we're probably looking for different things than a theorist would be looking at.
Right. Yeah. Thank you.
Then let me ask Professor Zvягin, please. Andrei Anatolyevich.
Thank you very much. I'm sorry for. Thank you very much for your very interesting talk, and I would like to clarify some point. In fact, monopoles are called here because these spins up and spins down are actually deconfined in these artificial spin ice and in the standard classical spin ice for parachutes and so on. So that's the point. In fact, that is why actually they move as some deconfined charge particles, like electric monopoles.
Right.
That is
I agree.
actually-
There is an analogy. I would say the analogy is
It's
a little
not
bit.
only it's not only analogy, because even if one takes into account the long range interactions like the magnetodipole interactions and so on, even in this case, these monopoles are deconfined, so they behave as free, almost free particles. In fact, for the real substances, this behavior is limited by the effective spins 1/2, so to say, the model of effective spin 1/2. In reality, these are rare earth compounds, of course.
Right.
And they behave as effective spins 1/2 with the Ising-like anisotropy only for low enough temperatures.
Right.
I just know it because I was involved in many works with, together with experimentalists also. I worked with Roderick Merkster. Maybe you know him.
But then
Roderick
maybe I can
Merkster.
ask you a question. Like, okay, so you're saying there are three particles. The reasons they move is that those individual spins flip. So every flip is statistically random.
But they appear as some line between them, right? As for real Dirac monopoles.
What is the sense of them being free particles? If I set it in motion, can I give it a momentum and it will continue moving with constant momentum, or that's some kind of different free particle?
They're not moving. They are created by pairs, of course, right? As natural for spins. You turn the spin. That is physical excitation, right? But then, if one move this this spin turn from one place to the other place on the lattice, on this lattice, for instance, for this artificial spin ice, for two-dimensional artificial spin ice, or real three-dimensional spin ice, you can see that there is no energy loss in this kind of movement. And in fact, you can move one side of this large spin, so to say, the North Pole. You can move from the South Pole to the infinite distance, and there will be no energy cost for this kind of
I think this
situation.
idea probably is accepted.
Yeah, I think in this
some-
spin ice there is some energy involved, but what we're looking at is the case where at the temperature we're working at, which is room temperature, KT is sufficient to let the
difference. Maybe the difference is because in this more realistic, so to say, spin ice, not in artificial spin ice, one has in reality real effective spins. Here you have islands,
yes,
these small islands which work as like spins, and their anisotropy is determined by their shape, right? As far as I remember,
by the shape, or if they're circular,
by the shape.
then it's
the shape of these small islands, right?
Yes,
that is a point, and that is why actually it determines the difference between this artificial spin ice and real spin ice.
Yeah,
that is a point, and that is why for this artificial spin ice, the dipole-dipole interaction is more essential.
Yes,
that is a point. But in reality, as far as I understand, it is not very important for the topic of your very interesting talk. Actually, you used this property just to have the application of this artificial spin ice as some mechanism to obtain some transfer of information in some quantum elementary quantum cells, right? Is it correct?
Well, they're not quantum cells, but classical cells. Yes, probabilistic cells. Yeah, maybe that's.
Yeah. Probabilistic cells. You just model the quantum cells as using this, so to say, artificial spin ice as a. That is, as far as I understand, that is the essence of your work.
Exactly.
And the most important point is that you have very long relaxation times for this system.
We can get
that is
relaxation
very
times.
important.
We're really just at the beginning of understanding how to create that, because we were so surprised with the canting and also with the rotational boat. So when you go from simple islands to something where there's a very, very small symmetry breaking field, it was only 8 Ersteds here, but it was enough to have a huge impact on the dynamics. And since most devices that would be electrically controlled would have a structure kind of similar to what we've got, we really want to understand this.
Mm-hmm. Yeah, that is actually, for me, it was absolutely clear from your very important, interesting talk. Thank you very much.
Thank you.
Yes, Yaroslav, please.
Okay, thank you. So I had a different question. How possible it is experimentally to measure the state of 2 different islands, have a microscope with 2 needles?
Oh, we would love to do that. Yes. We have, where is it? We have, in this case over here, we have actually measured 3 different devices at the same time. But you notice these devices are many microns apart from one another. They're not a few, 100 nanometers apart. You would have to do some sort of hardwiring to do this. You could not use a scanning probe. There was a company, 15 years ago, that came up with a device that had 4 scanning probes on it. But the idea was you'd be able to do 4-point probe measurements on nanostructures, but it was extremely difficult to operate the tips independently. And so you would really have to hardwire one. You could have one scanning probe and one fixed probe. And with our experiments with the neural network, we're going to hardwire the inputs and then use the single scanning probe to go through the lattice. So I think we can get 2 if we use this not as an input, but we just measure it as a function of time, and then we scan the second one. But it's not a trivial experiment.
Thanks.
It's for the next graduate student to work on.
Will we continue, Yaroslav?
No, thank you.
Then Andrei Anatольевич, please. Professor Zvagin.
I'm very sorry. I just mentioned perovskites, of course, not perovskites, but pyrachlors. Definitely.
Right, pyrachlors.
Real. I'm very sorry. That's all.
And now I would like to read what we have in chat. There's the gratitude to which I would like to join. Professor Majetich, please allow us to cordially thank you for your participation in the IEEE Magnetism for Ukraine grants. The audience is clapping, so probably it's time to finish our seminar. There's no more questions or comments. With this, I would like to acknowledge, to thank the audience, all the attendees, and Professor Majetich. Thank you so much for your nice talk and the discussion.
Thank you. And Slava Ukraini. Bye.
Stop. Bye-bye.
Very much.
Bye.
We'll see you next